Well, happy Babe Ruth Day. Now, I don't know when you're watching this, so I apologize if it's not Babe Ruth Day, but his birthday was, I believe, April 27th. So that's the day that I created this and have made this video. So I hope I was correct on that date. But anyway, Babe Ruth was a great baseball player, um, and he had all the stats to prove it. So there's some math connections there. You can do a lot with the stats of Babe Ruth. But anyway, we're not going to work with stats today. We're going to work with areas and volumes, and specifically areas and volumes of similar solids. So when you take a look at similar solids, our goal then is to compare and find areas and volumes, so surface areas specifically, and volumes of similar solids. So just looking at this picture here, we're not going to do this right now, but this might help thinking about scale factor. If we know the scale factor of the base would be 2 to 1. So meaning this would, if this is 2, this would be 1. Think about what the ratio of the area of that base would be, and then what's the ratio of the area of the volume of the figure. Not even giving you anything about the height or anything, just make a conjecture, a hypothesis, an educated guess. Because chances are if you remember what we talked about for the connection between similar solids with their scale factor, their perimeter, and their area, earlier on, you can hopefully look at that pattern and figure out the scale factor or the ratio of the volumes then as well. And that's what we're going to talk about today. So let's start it off. Similar solids. Similar solids have the same shape, and all their corresponding dimensions are proportional. I mean, they have that same scale factor, so that's key. Same shape, just not same size. The ratio of the corresponding linear dimensions of two similar solids is the scale factor. So it depends on how you look at it. But any two cubes are similar, and any two spheres are similar. So they all have similar dimensions, so they're going to be similar solids. A couple examples, let's just look at to see if we can figure out if they're similar or not. So they have to be the same shape. So if we look at example 1, we have two cylinders, and the corresponding dimensions are proportional. So really the only dimensions that we need to know are like the radius or diameter and the height. So are the cylinders similar? If so, what is the scale factor? So let's look at 6, and well, let's do 6 to 5 would be the radii. See if that ratio is the same as 12 to 10. And indeed it is. If you would reduce 12 tenths, it would be 6 fifths. So they are similar because they have the same, but they are proportional. The scale factor then, to get from 6 to 5, well, it would be 5/6 of it. So the scale factor, we can leave it as a fraction, would be 5/6 or 6 fifths. It depends on how you look at it. As long as you understand if you're going larger or smaller. All right, those are similar. There's a scale factor. Number 2, try this one on your own. Determine if they're similar. We have prisms. And if they are, what's the scale factor? Go ahead, try number 2. All right, so what I did is I found similar parts. So the height right here, 2 and 3, the base width or length would be 3 and 6 here in the blue, and then the other ones that are corresponding would be 2 and 3. We need to see if those are all proportional. So we have 2 to 3, we have 3 to 6, and we have 2 to 3 again. 2 to 3s are going to be the same, but 3 to 6 would reduce to 1/2 and not 2/3. So they are not truly all the same ratio. They're not proportional. They're not similar for this one. All right. And last one with this, we're going to look at a pyramid. We're going to look at the base element, the dimensions, and then the height as well, because then everything else comes from those. So what do you think? Example 3, if they'd be similar or not? Let's check it out. 7 and 14, so that length right there. 7 is to 14. See if that's the same ratio as this right here, 7 to 14. Well, yes, obviously it's the same exact one, so it is proportional. Would this be the same ratio? 5 to 10. Yes, it would be. That reduces. That is proportional. So, yes, they're similar. And the scale factor, it looks like, would be 7 to 14, which would be 1/2, or 14 to 7, which would be 2 over 1. Again, it depends on how you look at it. If you're going from the smaller one to the larger one, or the larger one to the smaller one. 1/2 or 2 over 1. So those are similar figures. Now we're going to look at this first theorem that we have for this section, Theorem 1112, the area and volume of similar solids theorem. So we figured out earlier on that if you have the scale factor, or the ratio of the sides of the two figures, the ratio of their corresponding areas is a squared to b squared. So a to b is just squared because it's two-dimensional. So maybe you can guess the ratio of their volumes, which is three-dimensional, is a cubed to b cubed. So if they have this certain scale factor of 2 to 1, then you have to cube the 2 and the 1 to find the scale factor of their, or the ratio of their volumes. So example 4 looks like we're asking for, it says the given prisms are similar. What is the scale factor of the smaller prism to the larger prism? Just the scale factor. So again, there's always the scale factor, or that would be the same as the ratio of their perimeters. The area ratio and the volume ratio. But right now we just have the area because it's surface area. So it's 150 from smaller to larger. So really we should flip it. But we'll do that after, to 294. So to find out, we'd really take the square root of each of those. I'm just wondering if there's anything we can reduce when we're doing that. So we could divide them both by, hold on for, alright, so I just thought of one. If you divide both of them by 6, divide both of them by 6, here we go, that would be 25 here over 49. And I'm just looking for things that would be perfect squares, because this would be, if area is the square, to find the scale factor, you take the opposite, so the square root of that. So that would be the square root of 25 over the square root of 49, which really is equal to 5 over 7. That made it easy for me. So the scale factor is 5/7. If you're going, I guess that'd be if you're going from bigger to smaller. So we'll actually say 7/5 if you're going from smaller to bigger. All right, let's do the next one. Cylinders. The given cylinders are similar. What is the scale factor of the smaller cylinders to the bigger cylinder? This time we're given the volume. So again, scale factor, area ratio, and volume ratio. We're given the volume ratio. So we have, this might work out because it'd be 64 pi to 125 pi. Alright. And actually, from smaller to bigger, we're going to do the opposite. We're going to do 125 to 64. I'm taking out the pi right away because those can cancel out. Really, you'd have pi here, but those cancel each other out. Remember, this is a cubed to b cubed. This would just be a to b. This would be a squared to b squared. So to find the scale factor, we'd take the cube root of that. So 125 over 64. I'm going to take the cube root of those. And it'll work out, I believe, for this one. Because 5 times 5 times 5 is 125. So that's going to be 5. I think 4 times 4 times 4. So 4 times 4 is 16 times 4 is 64. So it would be 4. So the scale factor is 5/4. Sweet. That works out nicely. If you wanted to find the area factor, you just square that. So you have 25 over 16. See how that works? You just square it, and if you cube it, you get to the volume factor. You might say, well, aren't they the same if you just reduce them? But no, reducing is not the same as taking square roots, because if you can't reduce 25/16. There's nothing you can divide both of them by to reduce them. So, one last one. Let's look at example 6 here. The surface area of two similar figures are given. The volume of the larger figure is given. Find the volume of the smaller figure. So again, we have the scale factor. We have the area ratio. We have the volume ratio. Whoa, stop moving on me here. So this is a to b. This is a squared to b squared. And this would be a cubed to b cubed. What we have is the area. The surface area would be the area factor. So um, let's just go like this, 36 to 225. I don't think that I'd be able to figure out the scale or the volume factor without first figuring out the scale factor. So I'm going to do that. I'm going to take the 36 225. To find the scale factor, you'd square root it. You do the opposite. So that would leave me with 6 over 15, I believe. So 6/15 would be that. To find the volume one, you'd cube it, because it's a cubed. So 6 cubed to 15 cubed. Because the area one would have been 6 squared to 15 squared. Volume would be 6 cubed to 15 cubed, which if I take my calculator out, 6 times 6 times 6 is 216. And 15 times 15 times 15 is going to be a big number, 3,375. We're going to leave it at that. That would be the volume scale factor. Now, here's the issue. It doesn't ask for the volume scale factor. It says the volume of the larger figure. So if the scale factor is 216, or 3375, and we have the volume of the larger figure, that would have to go on the bottom. We'd have to then use some cross multiplication, because it's got to be proportional if they're similar. All right, so cross multiplication, we'd have 3375 x equals whatever 216 times 750 is. 216 times 750 equals 16 or 162,000. I'm going to divide that by 3375. Okay, I did that wrong. Divided by 3375. And I get x equals, is that 48? Alright, that is a much smaller figure. I guess it looked like it from the surface area too. So the volume would be 48 meters cubed for the smaller one. Alright, multi-step problem there. It all stems from that original theorem though. If you can figure out using the scale factors of these similar figures, the scale factors and the volume factors. Here's one more that we're not going to go through, but if you want to take a look and try it on your own, that'd be great. What's given to you, it says the volumes of two similar figures are 128 meters cubed and 250 meters cubed. The surface area of the larger figure is 250. What's the surface area of the smaller figure? So again, we have the volumes this time, and we're going to want to figure out that scale factor so we can figure out the scale factor of the surface areas, and then use that to find the surface area of the larger one. So why don't you go ahead and try this one actually, and we will talk about it next time. But that's what I'm going to leave you with, that one. So be prepared with that one for next time. And if you'd like to try the error analyses, there's more than one. I'm missing one on here. But go for it. Those are good practices as well. And then just review the goal for today of comparing and finding areas and volumes of similar solids. It's really just that one concept to hone in on. And that is section 11.7. That's the last section for this chapter on volumes and surface areas. So have a great rest of your day.